All right, we're going to talk about scientific notation and how all this works with the electromagnetic spectrum activity that you're working on. So here goes scientific notation. I want to just get my pen up and running here. So anytime you come across a number that shows something like this, 5 times 10 to the 5th meters, or maybe it's something like 2.5 times 10 to the negative 13 hertz. Okay, these are probably two types of numbers that you might see, and this would be something in scientific notation. So if we look at this, this is really saying that this is 5 meters, okay? It's a lot of meters. So anytime that we see the exponent as a positive value, it means that this is a really big number, okay? So in other words, the shift of the decimal is going to be in this direction to show that it's a very big number, okay? It's the reverse when we start talking about something that's in a negative exponent. So a negative exponent means that it's something that's really small. So in this case, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2, 5. Okay, that's how many hertz we would be looking at. And so this is a really small number. So we're shifting the direction this way. Easy way to kind of think about this is that going this way on the number line is always positive and going this way is always negative. So we're shifting the decimal to make something smaller, or we're shifting it to make something bigger. So that's kind of how we handle scientific notation. When we start to look at applying our scientific notation to something else, this is where we get into our metric prefixes. Okay, because sometimes you'll see these numbers and instead of writing in scientific notation, they use a prefix to kind of talk about this. Now, traditionally, we've always seen these as prefixes. So we see the kilo, the hecto, the deca, and then we get into our base unit. Okay. And then we end up with our smaller ones, which would be our deci, our centi, and our milli. So again, this is kilo. This is a prefix that we could attach to a base. This is hecto. This is deca. This is deci. Okay, deci, and then centi, and then milli. And so we've traditionally stayed within these for a lot of the work that we've done in science, okay, to where this would be like the limitation that we've worked with. Now, base units are really just any type of a unit that we could put in here, like the meter, okay, gram, liter. So these are some of the traditional ones that we've seen, but we could use the untraditional ones like seconds. We could use volts. Okay, there's lots of different things that you could do, and you can just attach a prefix to any of these. So we could have like millivolts, or we could have centiseconds, and we could have deciliters, and we could have decagrams, and we could have hectometers. So these are all just prefixes that we could attach to this. Now, in most of this situation, again, we're always looking at things as to whether something is bigger or something is smaller. So these prefixes make things smaller. These prefixes say that we're very big. So when we look at the relationship, we say, well, how big is it to something else? So we usually put them in terms of a relationship like this, where I might say that if I go with a kilometer, so 1 kilometer is equivalent to how many meters? we would then figure out how many jumps we are away from the base. So it's 1 jump, 2 jump, 3 jumps. So there's 3 jumps, which is 1, 0, 2, 0, 3, 0. So kilometer is bigger, and it takes 1,000 meters to make that 1 kilometer. Now, when we get into extremely big or extremely small, this is where we have to add in a few more prefixes. Now, our prefixes that we like to talk about now are going to be things like mega and giga and tera. So these are extremely big prefixes, okay? And it's no different than when we get to extremely small prefixes like micro and nano and pico. So these are really small prefixes. Now the big difference is that when we get outside of the normal range that you've seen before, a jump counts for more. So to go from kilo to mega, this is going to be 3 zeros. And from mega to giga is 3 more zeros. And from giga to tera, it's 3 more zeros. So if we started to look at like a terabyte versus a byte, so 1 terabyte is really big. It would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bytes. Okay, so 1 terabyte is equal to that many bytes. And again, it's a really big number when we start to think about how many bytes make up 1 terabyte. Okay, when we go the other direction, these are really small, but again, same principle applies. It's 3 zeros. So a traditional one that you might have seen is looking at nanometers. Like nanometers are really small, and we compare them then to meters. So if I had 500 nanometers, I would say, well, how many meters is that? Okay, well, it would be a lot of them. It would be the same as saying if we had, let's see, so if I have 500 nanometers, oh, wait a second, let me do this. Let's just talk general terms first. If I'm looking at 1 meter, how many nanometers would that be? Okay, it would be 1, 1, 2, 3. That's the 3 jumps to get us to milli, micro, nano. So 1 meter is that many nanometers. So it's extremely, large number of nanometers to make 1 meter, because the meter is bigger than the small nanometer. Now, one other thing I want to just make a comment on before I leave this slide is the micro is kind of an odd one, because from a prefix point of view, we use this little symbol called mu. And so we would attach that in front of the meter. So micrometers or micrograms would all have that little symbol in front of it instead. So that's kind of the way that we look at those relationships, okay, and those prefixes. Well, let's go ahead and let's talk a little bit about doing those conversions now. So how do we set up and do a conversion with this? So let's go back to that problem that I just originally started, where I had 500 nanometers, and I wanted to get rid of the nanometers portion and get it in the meters portion. Now, this is the way I like to set up dimensional analysis. Is I always take whatever the starting point is. So this is my starting number right here. I'm going to make sure that I put nanometers on the bottom. I'm going to put meters on the top. Now, mathematically, what happens is the nanometers cancel and we get meters in the end. We always put a 1 next to the bigger of the two, and then we figure out how many we would need to have. So it'd be 1, 2, 3. That gets us to the milli. 4, 5, 6 gets us to micro. 7, 8, 9, that gets us to nano. So it would be that many. Now the math is going to be really easy here, because really what we're doing is we're shifting our decimal place. You can see that we're going to be dividing by a really big number, but it's with a 1 and it's all the zeros. So we're really shifting our decimal place the 9 spots that we would need to go. So if our decimal starts there, it's going to shift over 9 spots. So we'll see it as something really small because it's a small portion of a meter. It'd be 1, 2, 3, 4, 5, 6, 7, 8. Okay. Hold on. I think I got too many. 1, 2, 3, 4, 5, 6, 7. Let's see. Get this. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. 3, 4, 5, 6, 7. Oops, I got 10 in there. Hold on. So we're just going to shift our decimal over. Clean this up a little bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9 would be my shift over, and this would be my meters. Now again, we don't like to write this like this a lot, so we usually end up writing it in scientific notation. So this would be 5.00 times 10 to the negative 7th meters. Okay, so it's that shift of the decimal, making the small number. Okay, that's why it's a negative, and so that's how we would then do that conversion. We can do one to kind of show the other side of things here as well. So let's go ahead and do, maybe we'll do like that. So I've got a 256, okay, gigabyte drive, and I want to figure out how many bytes that is. So gigabytes go down here, bytes go here, and now I have to say, well, the gigabyte is bigger, so how much bigger? So it's 1, 2, 3, that gets us to the kilo. 5, 6, that gets us to mega. 7, 8, 9, that gets us to giga. So we got ourselves to gigabytes. Now again, from the math point of view, we're just multiplying by something that has a lot of zeros. So it's just going to be shifting our decimal. So it ends up being 256, and now we're just going to shift that decimal 9 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it moved in 9 zeros, and there's our bytes. Now, again, not conventionally liking to write that like that, so we use scientific notation. So we are going to move our decimal all the way up here in between the 2 and the 5. So it comes 2.56 times 10, okay, to the, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bytes. Okay, so we would have 2.56 times 10 to the 11th bytes. So that's kind of getting us into our conversions. Now, we're going to have to do math with some of these things. So this is going to be a key point here, is to look at your calculator and see how to actually work with these. If you have a Texas Instruments calculator and it's a scientific type one, you should have a key that's called the EE key, and you'll have to hit maybe the shift button to get to it. So you're looking for that kind of a key in order to use. But you're just going to enter in your values, 4.35. You hit your function, get your E, and then you put in your exponent. So what this is really saying is that our measurement, our 4.35, that's the measurement piece. And then this is the factor of 10 piece. So it's two different parts. So it's a measurement and a factor of 10. And so then we would go ahead and use that. And again, this times 10, okay, piece right here is really the EE key on a calculator. So you don't have to hit the times, you don't have to hit the 10, you don't have to hit the raised to the power of. It actually knows to do that. Now your calculator is probably going to kick out answers that would also have things like this. And that's going to just show you that this is, again, the measurement, and then this is your factor of 10. So it's kind of splitting it up so that you can look at that. Now, when we do some of this math, we're going to have two main triangles that I like to work with. And the first one is an energy relationship triangle. So the energy relationship triangle looks like this. Okay, so energy is going to be the top. And this is that energy that's associated with that portion of the wave. And then we're going to have a constant value. Now this is a constant value called Planck's constant. And this value never changes. So h is always equal to 4.135 times 10 to the negative 15th electron volt seconds. So that's a constant value. Okay, it's important that you realize that this is going to be a constant value that never changes. And so that's this corner of this triangle. Now when we start to look at the other corners of the triangle, this is where we're going to have our frequency. Okay, so this is our frequency. And frequency is going to be in hertz. So you need to have hertz in order to multiply times the Planck's constant so that you end up with your energy in the units of electron volts. Now you can do the same thing. If you had the energy, you could go back and figure out what your frequency is. But in that case, the energy would be over the frequency and you would then divide those two. So this is the way that that triangle kind of works. And you'd have to make sure that you're using your calculator correctly with all that scientific notation. So that's the energy triangle. Now sometimes we don't always have the frequency. So we have another triangle, that's our speed triangle. Now this is because light always travels at the same speed. So the speed is always going to be referred to as the speed of light. And this has a letter that we like to use. It's the letter C, and it's a constant value again. So it's a never-changing value. So C is always equal to 3.00 times 10 to the 8th meters per second. So again, constant value, never changes. This is kind of our key thing right there. Okay, all light wants to travel at that speed regardless of the type of light it is. Now, when we look at the speed, we're going to do this based on the wavelength and the frequency. So we'd say, well, what's the frequency? Okay, so this is our frequency. And this again is measured in hertz. Okay, so you'd have to have it in hertz in order for it to work. And then you'd have your wavelength, and that's that same symbol that we've seen before. And that's going to be in meters. So we would take this in meters. This is the wavelength. Okay, and so that's the way we kind of set those things up, is looking at them in terms of wavelengths and frequencies. And we would again multiply this one, or we would divide when we're over it. Okay, and we can set up these triangles, and this one actually should look familiar because this is the same set triangle that we used when we were talking about speed of sound. The only difference is that the speed of sound was not a constant. It changed, and so we had to accommodate for that change. You should have enough information now that you can kind of make sure that you're getting the electromagnetic spectrum slides put together well. And I also have for you today just 3 little quick problems that you're going to finish out this with, so you get a chance to practice all of the skills with your with these triangles. Okay, have a good day.